Hi everyone. Thank you for coming to this talk. Today I will present ICP exploiting instruction correlation for prefetching irregular memory accesses. This work is conducted by GL group at ISCA'26. Okay, let's start. Here is a roadmap for the talk. Let me start with temporal prefetchers. Temporal prefetchers work by learning correlations between memory addresses. In this example, at time t1, the memory access a sequence of address x0, s1, s2, and so on. The prefetcher records address level transitions such as x0 to x1, s1 to s2, and so on in a metadata table. Later, at time t2, if x0 appears again, the temporal prefetcher assumes that the same sequence will repeat. It can replace the recorded sequence and prefetch x1, s2, s3, and s4. The idea is powerful because it does not require a simple stride or stream patterns. As long as the same address sequence repeats, temporal prefetching can handle irregular accesses. However, temporal prefetchers face several fundamental limitations. The first limitation is that temporal prefetcher require address level repetitions. If the program later access x1, x0 followed by y1, y2, y3, and y4 instead of x1, s2, and so on, the metadata learned at T1 is no longer useful. In this case, the prefetcher either fails to prefetch the data that will be used, or it issues useless prefetches. This is not just a rare corner case. It commonly happens in indirect memory accesses, where the address depends on input data, so the dynamic addresses may change from one execution phase to another. The second limitation is metadata overhead. Even when address recurrence exists, the accessed address can be highly diverse. Since temporal prefetchers record address-to-address correlations, each dynamic address pair may require its own metadata entry. As the figure suggests, a program can easily generate thousands or millions of different address correlations. State-of-the-art temporal prefetchers need a very large metadata table, up to around 1 megabyte in SOTA designs. This is very expensive on chip, and it also complicates the cache hierarchy because the system has to reserve and manage a large space for the table. This case study shows the core opportunities behind ICP. In the loop, PC pre loads BI, then an add instruction computes the address of ABI, and PC sac loads ABI. If the function block is executed with different inputs, the actual address P1, P2, and so on for PC pre may never repeat. Similarly, the successor address S1, S2, and so on may also never repeat. This slide explains why temporal prefetching has a function failure on this pattern. Temporal prefetchers can only use a previously seen address to predict another previously seen address. But here, the address generated by PC-pre is in one iteration does not reappear later. And the address generated by PC-sac also change with the input. As a result, the address of PC-pre cannot be used as a reliable key to infer the future address of PC-sac. The problem is therefore more fundamental than insufficient table capacity. Even with a very large table, if the dynamic address do not repeat, the temporal prefetcher cannot trigger useful prefetches. The fix in ICP is to move from address level correlations to instruction level correlations. In the case study, PC SAC always follows PC press through the same data dependency relationship. So instead of remembering that a particular address PY was followed by S1, ICP remembers that the instruction PC press is correlated with the instruction PC SAC. When PC-prep executes against and its loaded value becomes available, ICP uses that value to speculatively execute the dependency chain and compute the address that the PC-SAC will access. In this way, ICP can prefetch PC-SAC even if none of the concrete memory addresses have appeared before. Instruction level correlation also significantly reduces metadata overhead. In this example, an address level temporal prefetcher may need to store one entry for each dynamic pair, such as P1 to S1, P2 to S2, and all the way to P100,000 to S100,000. Most of those entries are never reused if the address do not repeat. By contrast, ICP only need to store the static relationship between the PC pre and the PC SAC plus the short dependency path connecting them. A single instruction correlation can represent a very large number of dynamic address correlations. So this is a key reason ICP can be both more general and more storage efficient. This figure quantifies the metadata advantage. The y-axis is on log scale, and it compares temporal prefetchers with ICP across several irregular spec workloads. The results show that storing instruction level correlations achieves 1,000 times better metadata efficiency than temporal prefetcher. Now that we have seen the motivation, I will move to the overview of ICP. The main question is, what exactly does ICP learn and how does it turn a learned instruction correlation into an actual prefetch? I will first define the target pattern as a pair of correlated memory instructions, PC pre and PC SAC. Then I will show how this design generalized beyond traditional indirect prefetchers. ICP targets a memory instruction pair connected by a data dependency chain. We call the predecessor PC pre and the successor PC SAC. PC pre can be any load instruction, while PC SAC is an irregular load whose address depends directly or indirect on the value produced by PC pre. Once ICP has learned a PC pre to PC SAC correlation, it can use cache line responses to prefetch irregular accesses. When the cache line corresponding to PC pre returns, ICP read the data accessed by PC pre from that line. It then speculatively executes the dependency chain and compute the memory address that PC SAC will later access. A key point is that the triggering line can come from either a demand request or a prefetch request issued by any existing prefetchers. This lets ICP build on top of conventional prefetchers. So the basic prefetcher bring an prefetch line, and ICP use their return data to move further along the dependency chain and prefetch the harder irregular accesses. Compared with indirect prefetchers, ICP provides three forms of generalization. The first is a target. Traditional indirect prefetchers are mainly designed for nested array accesses. They typically assume that the inner access is a striding load and the outer access is array-based. ICP does not make this restriction. It directly targets any irregular loads that cause demand miss. after basic prefetcher have already handled simple patterns such as pointer chasing. The second generalization is a trigger source. Indirect prefetchers usually rely on a stride prefetcher to predict the future address of inner array load. This means their effectiveness is tightly coupled to stride-friendly inner accesses. ICP can instead use any cache line response associated with PC pre. If a line is brought by a stream, stride, or spatial prefetchers, ICP can use it. If no prefetcher brings the line early, ICP can still use the demand response. This makes ICP less dependent on one specific prefetcher and give it more opportunities to start computing the successor address early. The third generalization is the dependency chain itself. Indirect prefetchers are usually specialized for array indexing relationship. ICP records the intermediate instruction between PC-pre and PC-suck, and then speculative executes the recorded chains. The chain can include common address computation operations such as addition, shift, and logic operations. By supporting these simple dependent instructions, ICP can connect a wider variety of PC-pre and PC-suck pairs. At the same time, it avoids the complexity of run-ahead execution because it only executes a short filtered dependency path for prefetching. Now I will move to the evaluation. This figure shows performance speed up. The left group contains spec workloads, which are more friendly to temporal prefetchers. The middle group contains gap workloads, which are more friendly to indirect prefetchers. ICP provides performance comparable to the combined DMP plus triangle configuration while using much less storage. In the paper, ICP outperforms existing temporal prefetchers, indirect prefetchers, and run-ahead schemes across a large volume of benchmarks. This slide compares storage overhead against temporal prefetching. ICP require only about 400 bytes of correlation metadata and around 1.7 kilobyte of control state. By contrast, temporal prefetchers can require up to 1 megabyte of metadata storage plus about 17 kilobyte of control state. That is a major difference. ICP avoid dedicating a large fraction of LLC to metadata and avoid complex metadata insertion, replacement, and partitioning policies. This is one of the main practical advantages of storing instruction level correlations instead of address level correlations. This figure looks at metadata efficiency through the metadata reuse ratio. ICP achieve around 100,000 times higher metadata reuse ratio than Triangle. The reason is that each instruction correlation is reused across many dynamic executions. In contrast, temporal prefetcher metadata store concrete address correlations, which may be inserted but never reused when addresses do not recur. This result strongly supports the central argument that instruction level correlation is a more efficient representation for many irregular workloads. This slide compares ICP with indirect prefetchers in terms of correlation generalization. In the spec workload shown here, ICP captures substantially more correlations than previous indirect prefetchers touch and the DMP. The DMP bars are also split into solved and unsolved correlations, showing that even when a DMP can detect some relations, not all of them can be used by its prefetching mechanism. Run-ahead scheme can also compute future irregular memory accesses by speculative executing instructions. but they require much more instruction hardware support, such as CPU pipeline modifications. The ICP is much lighter. We are now at the conclusion. To summarize, ICP exploits instruction correlation to prefetch irregular memory accesses. Compared with temporal prefetchers, it's much more efficient in metadata overhead because one instruction level correlation can represent many dynamic address correlations. Compared with indirect prefetchers, ICP captures more general irregular memory accesses because it's not constrained to array patterns or striding loads. Compared with run-ahead execution, ICP introduced lower hardware complexity because it works mostly as a cache-side mechanism rather than a deeply integrated core mechanism. Overall, ICP is a compact and general approach for improving irregular memory access prefetching. Okay, thank you very much for your attention.